So today we're covering 11.2, which is probability. We're going to focus on two different ways to find probability. There's theoretical probability, which is where you have something that you're not actually doing like trials or experiments or anything like that. You're just looking at how many times something could happen. So when you set it up as a ratio, you're looking at the number of times something could happen over the total number of outcomes possible. And then for experimental probability, you're looking at, you're actually doing something. So you're actually like counting the number of people in a room or something like that. So a better way to think about it than the definition that's up there is the number of times an event actually occurs. And the event can be whatever you happen to be talking about. So you could be counting girls in the room, you could be counting number of red cars in the parking lot, and then that's over the total number of trials, or if you were talking about red cars in the parking lot, it would be out of like the total number of cars in the parking lot. Something like that. So problem number one is using experimental probability. And it says, of the 60 vehicles in a teacher's parking lot today, 15 are pickup trucks. What is the experimental probability that a vehicle in the lot is a pickup truck? So we're specifically looking at pickup trucks in this example. That's what we want to know, what the probability is that there's a pickup truck in the lot.
Wouldn't it just be 1/4?
So we're going to set it up as probability, and then just so we know what we're looking for, it's probability of pickup trucks. So we take how many pickup trucks we counted, which was 15, and we're putting that over the total number of vehicles, which is 60. So when we reduce this, you get 1/4. And you can also plug this into your calculator and get a decimal out, which would give you 0.25. And when we talk about probability, a lot of times it's easier to talk about it in percent. So to get percent from this, we're going to multiply this by 100, or just move the decimal place twice, so that you get 25%. So there's a 25% chance that a vehicle in the teacher's parking lot today is a pickup truck. That's what we're finding, or what we found. So the next example says, a softball player got a hit in 20 of her last 50 times at bat. What is the experimental probability that she will get a hit in her next at bat? So we're finding probability of a hit. So she's hit the ball 20 times out of her last 50. So our fraction that we're setting up is 20 out of 50. And again, you can reduce this so that it's 2/5, or you can get a decimal, which would be 0.4. And again, you can make that into a percent by moving the decimal twice or multiplying by 100, and you get 40%. So that's experimental probability. You actually are counting how many times she hit the ball or how many trucks were in the parking lot. So now problem 3 goes into theoretical probability. So we're supposed to find the theoretical probability of each event. So part A says, getting a 5 on one roll of a standard number cube. Now a standard number cube would be like a die. So what are your choices for when you roll a die? What are the choices or the possibilities that you could get? You can get 1 through 6. So I like to actually write down my whole set so I know what I'm looking at. So you have a possibility of getting a 1, a 2, a 3, a 4, a 5, or a 6. So part A is asking for probability of getting a 5. So if you roll the die once, how many times could you get a 5? Or how many ways could you get a 5? By rolling one die. You could only get it once, right? Because there's only one side that has a 5 on it. So your probability is 1 out of, you have 6 choices, or 6 different possibilities. So it's a 1 out of 6. And again, you could put that into a decimal, you could leave it as this fraction. I'll accept it either way. So then part B says, getting the sum of 5 on one roll of 2 standard number cubes. So now we're rolling 2 die, or 2 dice. And we want to know in how many different ways could we get a 5. So how many different ways can we get 5? What can we roll that equals 5? We could roll a 4 and a 1. What else can we roll? A 3 and a 2. What else? We rolled these 2. Now, if we rolled, say, the 4 first and then the 1, could we also roll a 1 first and then a 4? And that equals 5. And then the same thing with the second one, we could roll a 2 first and then a 3 second. So we actually have 4 different options of rolling a 5, or of getting the sum of 5. And then to find out what our entire set is, we have 2 die, and we had 6 choices with just 1. And now we have 6 more choices. But this goes back to the standard counting principle that we learned yesterday and on Monday. That, like, say you have 6 shirts and 6 pants, how many different outfits can you make? It's kind of the same thing. Now you have 6 choices for the first die and 6 choices for the second die. So you're going to take 6 times 6, which equals 36, and that equals your total possibilities. So now you know how many options you have for getting a sum of 5 and how many total you have. So the probability of getting a sum of 5 would be what? Setting up the fraction. You have 4 possibilities over 36. And then you can reduce that to 1 over 9. And again, you can put that in decimal form if you want. So now example 3 is practicing using these probabilities. So we're given a spinner that's divided into 8 equal regions, and they're numbered 1 through 8. And we need to find the theoretical probability of each event. So our entire set is this spinner that's divided with numbers 1 through 8. So the numbers 1 through 8 are our different options, make up our entire set. So for part A, it asks, what's the probability of getting less than 6? So how many choices do we have for getting less than 6? We have 5, right? We have 1, 2, 3, 4, and 5. So those are our possibilities for numbers that are less than 6. So our probability of getting less than 6 would equal these 5 choices divided by our entire set, or all of our options. So over 8. So now B is asking for the probability that it's a factor of 12. So what are our factors of 12 out of our original set? So 1 is a factor of 12, right? Because 12 times 1 is 12. 2 is a factor of 12. What else? 3 is a factor of 12. 4 and 6. So those are all our factors of 12 out of our original set. So the probability that it's a factor of 12 is what?
5 over 8.
It's 5 over 8 again, because we have 5 factors and our entire set was 8. Part C asks for multiples of 5, the probability of a multiple of 5. So how many multiples of 5 do we have?
2. 1 and 5.
Is 1 a multiple of 5?
No.
I think 5 is just our multiple of 5. Because it would be 5 times 1 is a multiple of 5. You don't, for that one, you don't really count the 1. Even though 1 times 5 is 5, it's not exactly what this is asking. That one's kind
See
of,
if you can divide 5 by that
Yeah.
number and get a whole number back out, that means that it's going to be
a multiple.
no multiple.
So for this one, we just have 5. So our probability of a multiple of 5
1/8.
is 1/8. And now for D, we have the probability of a prime number. Can somebody tell me what a prime number is? No one remembers what a prime number is? Alright, a prime number is a number that the only factors are 1 and itself. So 1 times itself are the only 2 factors for a prime number.
1, 3, 5, 7.
So 1, 3, 5, 7. Is that it? What about 2?
2 times 1 is 2.
Does 2 have any more factors? So isn't 2 a prime number too?
Yeah.
So probability of a prime number is 5/8 again. Now, depending on what you're looking at, sometimes different books won't classify 1 as a prime number, but for our purposes, we will classify it as a prime number. Just so you guys know. So the final kind of probability that we're going to talk about is geometric probability. And what geometric probability is talking about is you have a specific area that you're looking at out of a larger area. So that smaller area is what you're really interested in. And you want to know what the chances are of being in that area as opposed to being in the entire area. So example 5 provides a nice example of how to set this up. And it says a batter's strike zone depends on how high, on the height and the stance of the batter. What is the geometric probability that a baseball thrown at random within the batter's strike zone, as shown in the figure, will be a high inside strike? So it gives us that the batter's entire strike zone is this larger rectangle. And it gives us that the high strike zone is this small rectangle inside of the bigger strike zone. So it wants us to find the probability that it'll be in this smaller rectangle. So we're going to say P of the high strike equals, how do we find the area of this smaller rectangle? How do you find the area of a rectangle? Is length times height, or width times height, or one side times another side. However you can remember it, but it's the shorter side times the longer side, so length times width. So for this one, we're given 4, and we're given that the height is 6. And then we need to put that over the area of the entire region, which is our larger rectangle. So how would we find the area of our larger rectangle? 17 times 22. So when you put this in your calculator, you'll get a decimal, and you end up getting 0.064. And this would be one that it would be nice to put into a percentage. So when you multiply by 100, you get 6.4%. So a pitcher only has a 6.4% of getting it into this high strike zone. So our final example is another one pertaining to the geometric probability and using this batter's strike zone thing. So now it's saying that this batter's strike zone is 15 inches by 20 inches, and the high inside strike zone is 3 by 5. And it wants us to find the probability that it'll be in the high strike zone again. So we're going to set it up the same way we did our last example. So we need the area of the high strike zone. What's the area for the high strike zone in this one?
3 by 5.
It's a 3 by 5, so 3 times 5. And then what's the area of our entire strike zone?
15 times 20.
15 times 20. And we get 0.05, which translates to 5%. So for this batter, they have an even smaller percentage of having a strike put in that high strike zone. So the last page, front and back, is your homework. It will be on YouTube later today.